This video is an introduction to the topic of eigenvalues and eigenvectors for a square matrix A. You'll recall that when we talked about linear transformations from the beginning, we said that there was a small list of things that linear transformations can do geometrically. They can stretch and shrink, they can rotate, they can reflect, they can project, and they can shear. But there wasn't really a way back then for us to determine which of those linear transformation geometries a particular matrix represented. Eigenvalues and eigenvectors are going to be a way for us to get at the geometric characteristics of a square matrix. In other words, what does their linear transformation look like? The prefix eigen in German means characteristic, so it's going to tell us some fundamental property of a matrix A. How we're going to think about eigenvalues and eigenvectors is that we're going to think of eigenvalues, which generally are scalar numbers, usually real numbers, but as we'll see they might be complex as well. The eigenvalues of a matrix will represent stretching factors, the amount by which the matrix A stretches the length of a particular vector. And an eigenvector, that which is being stretched, we're going to think of those as describing the directions along which the matrix A stretches. If we represent the eigenvalue and eigenvalue of a matrix with the Greek letter lambda, and an eigenvector of that matrix with the vector v, then the equation which is going to describe the relationship between a matrix and its eigenvalues and eigenvectors is the equation A times v is equal to lambda times v. It's called the eigenvalue-eigenvector equation. In other words, this is an equation that's going to tell us which vectors, those are the v's, are getting stretched to be a multiple of themselves, and that multiple is lambda, by the linear transformation A. So where the first half of linear algebra is all about solving the matrix equation AX equals B, the second half of linear algebra tends to be about solving the eigenvalue-eigenvector equation, AV equals lambda V, to figure out which vectors are being stretched by the matrix A, and by how much. To illustrate the idea, let's take a look at this matrix A, having entries 1, -1, -2, 0. On this set of axes, we're going to be able to look at both a vector x, which is drawn in purple, and the vector A times x, which is visualized in green. Notice choosing different input vectors x gives us different output vectors b. What we're looking for is a vector which, when A multiplies that vector, the result, the image b, is a scalar multiple of x itself. Hunting around inside of the xy plane, we find our first example right about here. Notice that for this particular vector, x, when I multiply this vector by the matrix A, it sure looks like what happens is that this vector is getting sent into a multiple of itself. Namely, it looks as though this is just being stretched out. It looks roughly like the image is twice as long, but parallel to the source vector. We would say in this example that x is an eigenvector of the matrix A, and the eigenvalue associated with that eigenvector would be 2, the amount by which the matrix A is stretching out the vector x. Of course, defining an eigenvector for a matrix is actually not a very well-defined thing to do. After all, if the matrix A stretches this vector by a factor of 2, then necessarily, because of linearity, it also stretches any other vector that lies along that line by a factor of 2. So it stretches this vector, which looks like 5, -5, by a factor of 2. It also stretches this vector, -5, 5, by a factor of 2, and so forth and so forth. So eigenvectors, evidently, do not come in individual sets, but rather come in entire spaces, in fact, vector subspaces, of the domain and the codomain of this linear transformation. But at least we found one example now of a vector, actually a whole bunch of vectors, which are being stretched by the matrix A, it looks like by a factor of 2. In fact, if we compare the length of these vectors, one to another, we find out that the ratio of the length of the image to the length of the source is indeed approximately 2. So it looks like we found an eigenvector whose eigenvalue is equal to 2. Are there any other eigenvector-eigenvalue pairs for this matrix? To find out, we can hunt around some more. if we choose some different source vectors, we find out that besides this eigenvector direction that we found before, it looks like there's one more direction that satisfies that x is parallel to ax, that x is parallel to its image. And that looks like this direction. Notice here the purple x vector and the green a times x vector lie along the same line, even though they are in opposite directions this time. And if we spin it around to the other side, the same is true on that side as well. So we would say that this particular vector, whatever are the coordinates of this vector, this would also qualify as an eigenvector for A. And because when I multiply this vector by A, the result is -1 times that vector, we would say that this vector, x, is also an eigenvector of the matrix A, and its eigenvalue, in this example, is -1. Notice that having an eigenvalue of -1 has something to do with the fact that it looks like this matrix is reflecting this vector through the origin. So the conclusion we can make from this is that this matrix A has two different eigenvector-eigenvalue pairs. Namely, the first eigenvalue-eigenvector pair was the first one that we discovered, where the eigenvectors lied along this line, and the eigenvalue of the eigenvectors along this line was 2. Again, because the effect that A has on these vectors is that A stretches these vectors out by a factor of 2. Meanwhile, we discovered a second set of eigenvectors that lie along this line, and along that line we say the eigenvalue is -1, because the effect that A has when it multiplies vectors along that line is that it multiplies those vectors by -1. And so A multiplies these vectors by -1. What we want to do now is figure out how linear algebra can help us to discover the eigenvalues and eigenvectors for a particular matrix, and what are the different cases of how eigenvalues illustrate the geometry that a linear transformation has.